So again, I'm Travis Porter. I'm with the company about 17 years. I've done a lot through my time here. Initially started as a technician years ago. I came through the rankings through customer service, technical support. Did a pretty good stint in technical support about 10 years. And about 5 years ago now, I moved over into sales team. Where I currently reside as an inside sales account manager here. So again, you may hear from me if you're interested in purchasing anything down the road. Definitely can help you with that. All right, let's get rolling on our agenda. Again, today is just kind of types of calibration you can do. The first is going to be a electronics with a simulator. We're going to do an electronics and sensor in a dry well, and then we're also going to kind of do that same. So again, it'll be electronics and sensor in a dry well with a reference thermometer. So we're just going to keep kind of building on some pretty common techniques that folks use to calibrate probes, and then we'll have a quick kind of component versus system calibration review at the end. We won't have time to kind of drill in on that one. But again, that I think we do other presentations that kind of pick up and kind of jump in more of a deep dive on those topics. So let's get rolling. So, by comparison, so basically we're going to look at base simulator side and then a heat source side, and then we're going to actually also look at a heat source with a reference. Some of the things to remember as you're going through things with just a simulator. So electronics check only. The good thing about those gives you pretty much unlimited on temperature range, because most simulators will be able to simulate most RTD thermocouples, since you have quite a wide range and a variety of different types of sensors. The thing about them is it's pretty much instantaneous. It's just seconds to simulate that. And I guess we mentioned it's multifunction, so you could have PRTs, thermocouples, things like that. Using a heat source, you have to do the electronics and the sensor together. You can be limited by your temperature range, again, of the heat source. And it does take some time to get up to temperature in source. So again, we're also only measuring the temperature of the piece as a system. So one big note to remember is if you're doing calibration by simulation, it does not consider the temperature sensor. So typically, as we go through the example, you'll see more about that, because we're just connecting the sensor as we're simulating, calibrate the electron side. So again, we can run it. That's the only piece you're doing in a calibration. So again, we'll go through the do's and don'ts, pros and cons of each. All right, our example, we're going to calibrate, basically test and adjust an RTD handheld thermometer at 2 points. The points will be fairly nominal, 0 and 100 C, to keep it simple for us. After calibration, the thermometer should be accurate to -0.2 degrees C, and it should be traceable to NIST or an NMI. And so this is kind of the criteria we're going to set up in our potential or example here, just kind of to keep in the back of your mind, is this working, is this not working for what we're doing. So again, we're going to kind of review that as we run through the process and the techniques. Typically, in our scenario, as new, the meter was calibrated and it will conform to the DIN curve. So again, in our example, it's a readout and a PRT. So we're going to work with a probe that's a 100 ohm platinum. For this example, we could call it DIN class A, DIN class B. But again, we want to keep in mind we're going to be working with a 100 ohm probe. The resolution on our readout here is going to be 0.1, actually is plus minus 0.2, and again, we've got to rate or scale the unit. So in our example, we're going to pretend that we've got trim pots on the back, one for the low, one high. So we got a trim pot 1, trim pot 2. Just kind of simulating kind of some what we used to do here live in one of our sensor we used to have. So again, that's kind of where we pick up on this example. So simulator, how does it work? Well, basically, in this case, you disconnect your probe and you're going to connect the temperature simulator to your thermometer. So, it goes back to that note a few back of, be a potential error now not being considered by the probe. Simulator basically does what it's going to simulate the resistance of the probe. In our case, it's going to be ohms. And then the electronics piece of our thermometer is going to think it's seeing a probe. We're going to see, okay, is this working with the specs we think it is, or is it kind of out of tolerance? Calibrate, basically the electronics. You're going to take the input, or get something we just kind of discussed. Basically, we're simulating. In our case, where we're simulating an RTD probe, we're going to be working typically with a range of 100 ohms up to 138 ohms for our example here, because we are working with 0 to 100 C. So again, the nominal settings of a 100 ohm probe, typically 100, 0, and 138.5 at the 100 point. The other thing to consider with the simulator's role is it also can output other things besides just the RTD. We're notorious for having a wide range of thermocouples that you can select, and then in that case you would be simulating a millivoltage resistance, and then in some we also simulate thermistors. The thing to note about thermistors is it's a much higher resistance range. Most are nominally in about 25 C, about a 10 ohm. And these are all based off of typically national tables, either like the DIN class or AC or the graphs for the thermocouple. So as we're basically, we're going to disconnect the probe and we're going to connect our simulator. In this example below, I can see it's usually just a pretty simple solution or connection. We're simply unplugging and then reconnecting. Not there, again, really simple. The only thing to consider is with the thermocouples, I think you do have to have the appropriate type of plug. Again, if you're working with KHTs, that can give you a little bit of universal ones, which I think most can work well with. So again, just things like that to keep in mind on the simulator side when you're making the connection. Establish the connection. The root is pretty easy in our example. Again, we're only checking 2 points, the 0 and 100. And again, that was kind of our criteria for our example here. One thing that's really important as you're going through any calibrations is to record your as found readings. So next we're going to set the simulator to 0 C. The simulator now is going to generate 100 ohms, and we'll receive that as found reading. Then we'll move to the 100 degrees C, or roughly 138.5 ohms. And again, those are the ohms value based off of a typical DIN curve, and record that as well. So now we've established where we're at. Now we're going to go back and simulate 0 and make any adjustments needed to that first trim pot until we read right at 0. Then we again repeat the process and go to 100 degrees C and adjust the pot until it reads properly there. You may see a linear issue potentially where you adjust one pot up and it pulls your bottom reading down. Sometimes you may have to repeat steps a couple of times to kind of maybe limit the top down slightly, or you'll see a slightly high on your top end, and then it pulls 0 in potentially right where you need it to be. We'll discuss that a little bit further. The routines we're going to run through, again, are all hypothetical, kind of based on just kind of building upon each. The other thing to consider is running into the linear slope issue where, say, you adjust 0 right at 0, and then we go to 100 and we trim that one right in at 100, and then come back to 0 and we're out. Again, remember in our example, we were trying to hold to a plus minus 0.2. Again, there's somewhere along that slope that is giving us a little bit of issue there. So since even the adjustments at 0, 100, sometimes it's good to kind of check some midpoints, say 50 or even 25, 50, and 75, and again, to kind of see where you're drifting in that slope. So since we're trying to hold to a plus minus 0.2, we may have to slightly, say, in that example, adjust one fan up or down slightly to where we get a known error of, say, a 0.05 or maybe even a 0.1 to get that bottom end to come in to where we need it to be. So keep that in mind, because again, in a perfect world, everything would be great slope, and you'd adjust 0 and you'd hit 100, and it would be perfect. Oh, okay. Can you still hear me? Our technical difficulties this morning. Yep, looks like we're live. Yep, okay, I guess John dropped off on our audio. All right. So example where we've made this simulated adjustment at 0 and 100. Things to kind of keep in mind, could the calculation we just performed be considered traceable to NIST? And again, kind of a deeper discussion. If it wasn't, what would we have to do to make that possible? And what would be the future steps if we wanted to make the whole thermometer traceable? In our case, we simply just did one piece of it. So again, the questionable piece at this time is the probe. And from the few slides back, we stated that 75% potentially of the error could be contributed by potentially a bad probe if it's in your process. So even if you're reading the resistance very accurately, you could still have a probe that's not conforming to that curve that we wanted to see at. So again, if we were to make this something truly traceable, we would definitely have to put both pieces together and do a calibration that way. So again, that's more we'll build on going forward. But again, really quick pros and cons with the simulator. It's very fast. Once we program it, we're going to get the distance that we need. We can make our measurements and our adjustments. Again, another thing that's good about this is if you're adjusting and you're using known good probes, say you could have multiple class probes that you're working with, and you single readout with a few different probes that are left in a process potentially, and you just take your readout and plug in and get your readings. Again, some of the cons though, we can kind of get everything in that simulation. We can simulate both the probe and the readout together. So again, we've still got that unknown of the probe that it was not addressed in the simulation calibration that we did on just the electronics. So in our case, for argument, the calibration that we perform would not be considered traceable, again, because of that missing piece on the probe side. We're going to move on kind of to the next level, doing calibration, but this time instead of simulating, we're actually going to use a source. So in this case, we're going to use a heat source. A lot of times you'll hear these, the termination is a dry well, or dry bath has also been thrown around over the years. We also call our newer products metrology wells because we've kind of gone above and beyond what a typical dry well does in that we kind of spec them with an axial and radial gradient specs. So again, you'll hear a few different terms on the sources, but in this case again, for the sake of argument, let's pretend our heat source or our dry well is a tool with a 0.05 display accuracy. So in this case, you can see our setup. We're going to now use or leave the thermometer and probe connected and then place them in the well. The idea here, if you see the picture on the far right, in a dry well, you have the probes fully immersed. The idea with any dry well application the probe that you're testing as close as you can, which is usually full immersion in the dry well that you're using as the source. Reason for this is if you were to say you had a very short probe, say a couple of inches, and your probe not go all the way down to the bottom, you can experience a pretty significant gradient error that you not account for with that particular type of error. So again, things to consider there. There are workarounds using a reference probe, and I'll touch on those a little bit later as we keep going forward. So to get this set up, again, very simple. We're not disconnecting the probe from the readout now. We're simply just placing them in the well. One thing to consider as well when you're using a dry well is you really want a good fit on the probe. So if you have a 1/4 inch probe, use the appropriate 1/4 inch drilled well for that to get really good thermal conductivity between the heat source itself and the probe. Again, if you were to use, say, a 1/2 inch hole with a 1/4 inch probe or a 3/8 hole, you're going to leave some room for air with the air gap, which will cause an insulating effect, which typically causes your readings to read low versus the accuracy that you're hoping to kind of rest to. Right, very similar steps from the simulation in this process. Well, again, similar as far as the steps compared to the simulation we just did. Again, we're going to place the thermometer in the well. Typically, a lot of folks, and again, too, when I was a tech, we like to go cold to hot and then back. Usually, it's a little bit quicker for most units to move from the colder temperatures to the hotter temperatures as far as a heat source goes. So we would place the thermometer and probe in the well, set to 0. Allow the dry well to come down to temp and stabilize. So you'd want to check the specs on this. Again, just because the display is now reading what you think it is, it's always good to allow maybe 5 to 10 minutes once you've reached temperatures to just let everything kind of equilibrate. Then you take your as-found reading of the system, and then we're just going to simply set the dry well up to 100, and then you're going to move, come up temp, stabilize again, and then we will take the as-found reading there at 100 as well. Once we've done that, now we go back to the 0 point. So again, we've now recorded our as-found, or what we are currently at, and go to 0. As the trim, again, as an example, until we get it to read appropriate. Again, we'll adjust till we see 0, and then we'll move to the second set point again of 100C and adjust that pot as well. Same thing here on that linear slope. If you're not seeing what you want, or you're adjusting one and then you go back and it pulls the other one out, sometimes you do have to split that difference on slope. Again, too, a lot of times as you're ramping up and down in temperature, folks will, some midpoint, say a 50 check, or even 75, 50, and 25, just to kind of see where it's kind of pulling out on the tolerance. And again, too, it's always good between more data is always better than less. Again, excuse me, there are some things there, again, too, especially if it's costing you time. So again, always a balance. But it's good to get additional data if you're wanting to really see where you're potentially pulling out of that window that you want to be in. Again, in our example, we were trying to stick within that plus minus 0.2, which is we're down at 0 and we're getting a 0.1, but then at the top end we're only seeing a 99.9. We're still within that window that we want to be in, but you can see how the slope may, the top may affect the bottom. So again, things to keep in mind there as you're doing these calibrations. In the example, could it here be considered traceable? Again, the second question, is what we need to know to make it true or possible. So again, with the little warning here, you might need a little more information. kind of the warning goes back to knowing what your heat source is. And if your heat source in this example was did with a traceable calibration, then basically your calibration could be considered traceable because, again, you're just using the heat source now as your transfer standard to the thermometer. So again, you can prove that unbroken chain through the thermometer went to the heat source. The heat source is now calibrated. I've got this supplied documentation with it showing its traceability up and so forth. So again, that's if the heat source was not traceable in a particular example, our calibration would not be considered traceable. All right, kind of the real quick pros and cons of the dry well method. Calibrated as a system. We're using temperature, and again, it's really simple to set up. Again, you're just again matching your probe basically to an insert size, and then you're off and running. And some of the cons that you may run into doing the method, again, it's all kind of balancing what is required by your thermometer readout versus what's available in the different units. Different dry wells do have varying accuracy limit. And again, one of the cons we discussed is if your probe, or if you've got a unique situation where your probe is not able to be fully immersed into your well, again, can add some additional air that's really hard to quantify. And then with any system calibration that you do with a probe and readout, once you mate them and make adjustments, they're kind of mated for life. We've made the adjustments. Any error that might potentially be compensated by the electronics or the probe, and we've kind of nulled them out. It's not easy to say, okay, we took a quarter of the degree out of the electronics and a quarter of the degree error out of the probe. So again, as kind of everything got nulled in that system setup, we made the adjustment. The other thing is, too, depending upon the type of well you have, there may be some additional time required to get to the various temperature points and then stabilize to take your readings or your data and adjustments. All right, now we're just going to build upon that process again. So we've gone from a simulation to a actual well, and now we're going to go to an actual well calibration with a reference thermometer. One thing to consider here, again, we go back to that question, would this be considered traceable? This is one way to work around if your heat source is not traceable. So again, depending upon what equipment you may have access to, a lot of folks will have their gold standard, which may be the external reference and probe that they use in all of their processes, and then the heat sources become that. They're just a source of heat. The temperature of the heat source then kind of becomes a moot point, as it is kind of a nominal setting, because we're actually going to be referencing to the known, which would be their external reference thermometer, which they consider their gold standard for those, and they will keep and maintain quality on those pieces of equipment. So this example, you can show we've set this up again. We've got the external reference thermometer in the well. We've got a unit in test in the well is immersed fully at the bottom. Again, this kind of gives you kind of a break that maybe our dry well thinks it's a 100, our UUT might think it is 100.2. In reality, we're seeing 100.568, which is what we would be calling true temperature for the particular calibration method. The steps that we do, very similar. We're going to set the heat source down, have the units in the chamber or well, on it down, record sound data, run it back up to 100, get that as sound data, go down to 0, make any adjustments that we need, and then again run it up to the temperature, making that adjustment at the high end. To that slope applies. Again, some experiences as heck, you think everything should be linear, but again, sometimes you have to give up a little on your top or bottom end to pull the opposite end. It's the range or the accuracy that you're looking for. Again, kind of through these steps, again, they're all very similar. But again, more data, again, a lot of folks will add there a midpoint, say 50C or even 75 and 25, just to kind of see some incremental steps and kind of make sure that they're kind of staying within that 0.2 accuracy for our example that we've worked with at those different data points as well. Down, and then again, a lot of times folks will do just a quick check. Every time you make an adjustment, you should again validate that adjustment. Again, just don't go back to zero and say, okay, I've tweaked it at zero, and I know 100 was good last time I looked at it. Again, anytime you make a change, you have to go back through and revalidate any potential across range that you're working. All right. So some pros and cons when you're doing this technique with a reference thermometer. And you're typically going to get the best accuracy. Most external reference probes will go through their own process, which is usually held to a pretty high standard. Calibration is traceable, is right to the reference again, standard, whatever you want to call it for the particular lab. I've heard it called many things in various situations. Sometimes with these reference thermometers, it gives you some versatility. If you are particularly calibrating just quarter-inch probes or eighth-inch probes, you can get a reference probe that matches ideally to your sensors. That gives you kind of a better fit with the reference. Again, cons, as you add more equipment, your expenses usually go up. And then again, we're using 2 instruments down the setup as well and a reference. Again, pros, you're typically getting a better calibration. With these, time is always, time is money. So again, there are some delta in waiting for temperature changes to happen across the range, depending on how many data points you're taking. So those were kind of the 3 different techniques where we kind of built on a simulation, and then a source only, and then a heat source with a reference. Going to kind of review really quick. We're not going to have too much time to really dive deep into these component versus system calibrations, but I just wanted to touch on them briefly. So a component calibration, calibrated in a conventional manner, and the readout. Again, in our examples that we went through, most of the time things were together as a system for the heat source calibration and the heat source against the reference. The only time that we broke it apart was in the initial one with the simulation. So with a component what the other piece that was not shown there is the probe would go off and be placed through its own kind of routine where we would plug into another readout. Typically, it would go to a reference. Some adjustments would be made, or a polynomial fit, or we would ensure that it's conforming to a DIN class curve. That, as you each piece back, you now know, okay, my RTD probe is behaving how it's supposed to, and my readout electronics are adjusted within the tolerance they're supposed to be good at. So those examples with the component where you're calibrating each component, you can kind of use each piece as needed and plug other probes and readouts as needed. Again, once you've got 2 knowns, basically I've got known goods on both pieces, the readout and the probe. They become a little more versatile in moving them around the lab and using them in different applications. With the system calibration, that's where we connect a probe to readout, and this does happen even with some of the reference probes that come through our labs. Being a tech and kind of knowing what you may be up against, not particularly my favorite method, but they work well. There's nothing bad, and you lose some of the versatility as far as being able to interchange another probe with that same readout. So again, once you do a system calibration, these 2 pieces are locked together. We're not, splitting them apart and taking a hard look at each one. What typically happens in a system calibration is any error that's being contributed through the probe piece gets sold out on the electronic side of the readout piece. They just got this one link that we've calibrated across the board. So again, any kind of the flexibility if you had multiple probes that you use in a different application. So again, the flexibility would apply to both pieces in that particular case. So again, I'm going to touch on those really quick. Some pros and cons between the two. I've kind of touched on them as I've been speaking. You're getting kind of the best hard look at each piece. Uncertainties are, in my opinion, easy to define, and again, typically more robust. So you'll say, okay, we did this calibration on the probe, it went through this process comparison. The uncertainty on the comparison piece based on the reference equipment is X. And again, with the reason we go through the calibration compared against typically standard resistors, make offsets to those to make sure they're reading within the specs needed. And that way you've got two very versatile pieces that can be used with multiple probes and readouts. Some of the cost of that, again, you got two calibrations. Obviously, your cost goes up a little bit. Some of the time, folks don't like, say on the readout side, you don't get data in temperature. It's usually a parts per million, or a voltage, or a resistance, and a plus minus. So again, that makes it a little more difficult trying to interpret the results. So again, if you're not familiar with saying, okay, how do I take 20 parts per million accuracy and converting it to a temperature, that's something you'd have to be able to talk to with an auditor, and I've seen a few folks move simply towards the system calibrations to that. And again, with a system calibration, as we jump over to the pros and cons here of that one, the MGBs become less difficult to talk to because we've got just a single piece that we're saying, okay, this probe and route source is compared to our standard was X, here's the error, and we corrected it, now it's this. So it's much more clean for an auditor, usually simplifies the process a little bit for them. Some of the probes, again, they're a little bit less expensive. Data is going to be in temperature units versus a resistance cal versus a decal that you may see on the probe side. The thing that's kind of a con too is when you kind of lack the robustness. So again, when system calibration, it's really hard to define which piece is contributing to the error because each piece we're just kind of nulling across the playing field, and we don't care if a degree of the error is coming from the probe or point coming from the readout. We're just going to zero or basically put in the electronics of the readout alone. So again, something to keep in mind there as you go through the various types of actions that can be performed. And again, sometimes system calibrations are not offered for particular pieces because they do require a higher level of uncertainties, and so the process does not allow for that. Just basically could be quantified for, or we can't get the uncertainty to quantify for it in a particular process. So just things to keep in mind as you're doing your calibration work. I think coming up here, we've got a couple of future web seminars, but John's going to talk to these, and then I think we'll jump into our Q&A session here.
Thank you, Travis. I want to announce, before I do that, I just want to thank you for participating in this seminar. We have just concluded the presentation portion of the seminar, and we are now entering the question and answer session. If you question and haven't submitted it yet, feel free to do so at this time, and we would like to address all of them. Over 100 people joined the session from around the world, and they're going to again thank you for participating. Web seminars. I have on June 1st a web seminar called Let's Talk About Temperature Measurement with Fluke metrologist Mike Coleman, and presents some basic topics, and then there will be longer than normal question and answer session. 15th, there's a session called How to Calibrate a Metrology Well. This is the latest schedule. Please visit our website at fluke.com/cal-7. Also, one other thing I'd like to make you aware of is that we have an infrared calibration course coming up. It is on-site here in American Fork, Utah, in the United States. It will it's also a session on practical temperature calibration that runs here in American Fork, September 20th through the 22nd. Information on that, feel free to go to our website at flukecal.com/tempcal_training. Okay, if you are not subscribed to Fluke Calibration's email list, please feel free to do so at flukecal.com/sign-up. We're beginning the question and answer session at this time, so Travis, I'll read them off. Let's see. Question. Randall. On the thermocouple sets that Fluke sends out with 5522A, does Fluke have a specification on how accurate the thermocouples are?
To defer on that one, I'm not familiar with what's being sent out with 5522A. It kind of comes from my colleagues on the electric side. What I do know is that most of the Fluke Pro we do sell thermocouples are usually the 80PK series, and most of those are just the standard limit variable type thermocouples. Usually the limits on those are typically, I think, 0.75% of reading, or typically 0.1 degrees C, whatever is greater. Again, I'd have to double check with that on the electrical side. The next question comes from Paul A., who's Amatech in Kenya. That method is not applicable for other temperature sensors like IR thermometers and mercury and glass, right? And so which other method would be used? Okay, so that's kind of a two-part question. So you are correct. The method we described today would not apply to infrared thermometers. That you would need some sort of an infrared source. I don't know if you've looked at any of ours. You could review our 9132 and our 9133, as well as our 4180 and 81. They'll be more appropriate as a reference source for an IR thermometer. As far as mercury and glass thermometers, typically from what I've seen for best results, those ones are counted in a liquid bath using a similar technique that we did in the last one. So you would have a liquid bath with a reference and then your mercury thermometers in the liquid bath. And that's typically due to the mercury thermometer designs, whether they're a full immersion or partial immersion design. I guess folks will use a liquid bath for those that's appropriate for the range testing.
Next question comes from Mauricio. Is recommended time for stabilization? How do you that stabilization achieved?
So today with most dry wells, they will give a stabilization time specification. Again, most of the time it can be anywhere from 10 to 15 minutes. The biggest things that I've seen impact that is if you run a dry well to temperature, say you're running to 100 degrees, and now you take an ambient probe and place in that. So basically, you've now added a cold mass to that unit. So it's going to take some time for that block to recover from the cold ambient temperature probe and then come back up to temp and stabilize. So again, most of the time, though, it's fairly quick with a dry well. They recover pretty quick, and I think most folks hedge on the stabilization time when they say 10 to 20 minutes. But again, just watching your readings, again, your probe, you can kind of see when you come into a source, you'll kind of get that blip, and then it'll come back up and level out. When you start seeing that level out and you remain cold, then you can assume you're stable.
Okay, question from some PM2. What is the temperature difference between the reference sensor to the unit under test and a typical dry wells to maintain for uncertainty budget?
My best to kind of ask that. So again, it all comes down to the types of units that you're using. So again, there are different grades of dry wells, ranging from industrial types that will have much wider uncertainties. You could be as wide as ±1 to that tighten that up and get all the way into the point ones or less. So again, it's just kind of the range or the type of dry well. Again, this is the same with your units under test and a reference. There's different grades of PRTs and types and how they were calibrated, which will kind of various certainties based on the combination between the probe, the readout, and the heat source. So you would just want to do your homework as far as exploring the temperature range that you need versus your overall uncertainty that you're trying to adhere to, and then kind of build around that.
Lucio, is the time for stabilization? How stabilization has been achieved?
Kind of I think a little bit of a repeat again. Most dry wells will give us spec, and again, can be anywhere from 10 to 15 minutes or 10 to 20 minutes for stabilization once the temperature is reached. If you are monitoring it with a reference, sometimes you can just look at your average or your standard deviation once you've reached the temperature and kind of watch your readings on your reference probe. Again, for most dry wells, again, rule of thumb would be 10 to 20 minutes there once you've hit the temperature to full stability. Again, that's kind of a hedge bet, so to speak. Most of them are pretty quick to come up with stabilize.
Another question from PM2. What is to stabilize in between changing the data point between 0 degree and 100 degrees for a dry well?
It all be specific to the dry well and what the capacity of the unit is. Some of our units that have got fairly large capacity can move fairly rapidly between temperatures, just taking a few minutes. The smaller ones that go both hot and cold may take a little bit longer. Again, that's an effect you can look for with dry wells. Is usually I'll say time from ambient to use max temp or time from ambient to their min temp and kind of base your time for those.
Next is from Sergey. Any Fluke precision device that combines both methods of calibration, dry and electrical?
That I know of. We do have a few multi-function devices, even higher end ones, where you can, I guess, from my experience, you can use, say, some of our 754 series with a reference probe to drive a heat source, and then the 754 would also do electric simulation. So again, we would want to definitely drill down on what we're looking to do specifically in the various applications and then kind of make a recommendation there. But as far as what you're asking there, there isn't a unit that's like a dry well with an electrical simulator built into that. We do have some metrology wells with what they call our process option. It's more so to plug in UUTs, not so much to simulate them. But to some of our multifunction units, like our 26A would be one you may want to look at, and the 754B may give you what you're looking for, not 100%, but they do have options to plug in a reference and then communicate with different units. And really, just add-ons you can do to do pressure or electrical or temperature. But again, there isn't like a box that's a simulator then and also a heat source.
Next question from Patrick. For house of overall accuracy and lowest uncertainties, based on your experience, is component or some calibration preferred? Or can achieve with both?
We achieved with both. So again, we do offer system calibrations on a reference that are as good as individual component calibrations. Biggest beef being a technician is if you go with system cal, say the probe dropped, well, now the entire system's shot and it's got to go back and be checked. Whereas if you have ones with component calibrations and the probe dropped and you got a backup, you simply disconnect and reconnect and you're back on your way while you send that unit out. Again, you can do the same or close to the same uncertainty. It's just the flexibility of the units kind of gets trimmed down once you mate together.
Question comes from Randall. When checking these surface probes at around 65 degrees Fahrenheit to 90 degrees, what do you use as a source, and what probe would you calibrate them with? We use any chamber with a Fluke 5628 and STD probe and Omega surface probes wrapped in aluminum foil.
Okay. Again, surface probes are very difficult in that you're calibrating them as they're intended for use. You're only ever getting typically 50% at best contact on the surface. Again, it sounds like you've come up with kind of a homegrown solution there, which is great. It sounds like you're adding some thermal mass or you're wrapping them around the heat source to insulate them with the aluminum foil to kind of prevent that other 50% being impacted by the ambient, which is good. Again, you want to provide some insulation. From everything that I've been taught, if you can immerse probe, it's a surface probe, if you can get full immersion, say in a dry well or a bath, it's going to net you the best results versus a operation. But again, that's not always possible. So again, sometimes like you're doing here, you do have to get creative. The biggest thing to consider when you're doing these or coming up with these techniques is just to ensure that you do them, the process can be repeated. So just make sure you're getting good consistency and good repeatability in your process.
Okay, question from PM2. LC for sensor with dry wells. How do you get a good, acceptable result?
I'm not familiar with ILC, what you're referencing there. Some sort of log circuit. Might be a good one if you expand. Happy to kind of take that one offline and kind of dig into that for you. But again, I'm not familiar enough with what you're referencing to get a good answer. Again, that one, happy to take offline if you want to send me some more details via email.
Next from Stolt. should the probe be the same size, diameter, or length?
Yes, the closer your reference is matched to your units under test, the better your results will be, in that you're going to be roughly mimicking the same size and mass as your units under test. So, yes, it is possible. Match those. And again, that's always something you can do, but if it is possible, definitely do it, and it will get you.
Question from Angie. Currently use of Fluke 9103 drive well with the V insert. We would lay an insert with 6 to 8 inch holes, but have not been able to locate one. Is this that Fluke carries, or would we need to purchase the blank?
You know what, that we sell blank inserts that are already pre-milled with the appropriate outer dimensions, and then you could take that somewhere locally and have the the one holes milled in it. We also do custom inserts. The model for that one is a 3103-Y. Again, 3103-Y. That's something you could talk to your rep about and bring us get you up a kind of a drawing, and we mill that out for you. Time does take a little bit longer than our standard ones because we don't stock them. Really ask us about it, but we can assist with that.
Okay. I think follow up from Randall from earlier, but he says the RTD surface probes are Omega ON-409-PP with accuracy of plus or minus 0.1 degrees Celsius. And then he follows that up with a comment that says total immersion thermometers done in chambers vertical during calibration. Chambers are small to keep them vertical.
Not being familiar with the Omega model offhand, happy to take that one offline, Randall. I can follow up with you here offline, and we can kind of dig in on that one and kind of review some of the best practices.
Next is from Kiplingett. Doesn't matter of the probe affect the calibration result. So on the time taken for the drive well to cool down for next measurement, would it be tedious to constantly wait for the well to cool?
The probe diameter can affect your calibration results, and that's due to immersion. So again, there's a couple of rule of thumbs out there for immersion. One is to get proper immersion, you take 15 times the diameter of your probe plus of the sensor. The other rule of thumb that gets thrown around a lot is just straight up 20 times the diameter of your probe. Typically on a quarter-inch probe, that depending you go with, you end up with about a 5 to 6 inch immersion depth required to kind of negate any semiconduction errors you might experience. It does take some time again to wait for the next measurement, but again, just kind of some of the trade-offs. A lot of folks in the various calibration labs across, depending upon their throughput, they have a couple of drive wells, so they've got one that sits continuously at 0 and one at 100, and they just move between the two. So there's kind of a balance based on the application. In our example, it was kind of a one-off. And if you're doing some serious throughput, there are better ways to improve that, where you can move to 2 or 3 dry wells that are set at specific points that you just move the probes between. That way you're basically eliminating some of that wait time.
Question. What recommended recap period for RTDs and sensors? Is there a table to share?
Table to share. Most folks will base around kind of some sort of internal K process. It's usually based on some sort of risk versus recall type scenario. If that's not there, a lot of us just calibrate annually. And depending upon what you're doing, again, it kind of comes down to what's it going to cost me if my reference goes out of calibration before I catch it. So usually, again, it goes back to that risk versus recall. Again, most folks are on some sort of a calibration cycle.
Okay. Do you wish to share and explain about the proficiency test for sensors of various types?
On that one would be a great question for Mike on the next seminar. And while I mentioned his name again too, I would encourage any of you that if you can get on a seminar with Mike to do it. He's got a vast knowledge base because again he's been working in lab almost since I've known him here. Again, don't have on proficiency testing specifics, but might be able to shed some additional information on that.